Welcome to Learn with us. This is the 29th lecture of Basic Electronics.
First, we will have a quick review of our previous lecture. In your last lecture, you studied about N-type and P-type MOSFETs. You also understood current voltage characteristic curve of MOSFETs. You studied that there are three regions of operation in MOSFETs. First region is cutoff region, second region is saturation region, and third region is triode region. In your previous lecture, you also understood voltages in all these three regions, and you also studied about currents in all these three regions of operation. Now, what are the learning objectives of this lecture? In this lecture, you will solve some examples related to MOSFETs, and you will also understand the difference between different transconductance parameters. One is MOSFET transconductance parameter and second is process transconductance parameter. Now look at this example. If you have a transistor configuration like this, the arrow is here, it means it is N-type MOSFET, and here we have gate, and here we have VGG, and here we have VDD, and for suppose it is 5 volts and this VDD is also 5 volts, and here we have RD, and this is the direction of drain current, and as you can see here this source terminal is grounded. Now if the value of K is 0.5 milliamperes per volts square and the value of drain voltage is 0.1 volt and the value of threshold voltage is 1 volt. Okay, now how you are going to start your analysis? First we will find gate voltage. As you can see here, we don't have any gate resistor. It means here VGG is equal to VG, which is equal to 5 volts. Okay, we'll have gate voltage here. Here we have source voltage and here we have drain voltage. Okay, now we will find region of operation of transistor. Okay, we know that in saturation region gate to drain voltage is less than threshold voltage. This gate to drain voltage can be written as gate voltage minus drain voltage, and it is less than threshold voltage. Okay, now here we know that this gate voltage is 5 volts and this drain voltage is 0.1 volts and this threshold voltage is 1 volts, and here we have 4.9 volts which is less than here 1 volt. Now as you can see here, this condition of saturation region is not satisfied, but we know that this is the condition for triode region. It means here transistor is in triode region of operation because here gate to drain voltage is greater than threshold voltage. Okay, now we will find drain current ID. We know that the equation of drain current for triode region is ID is equal to K, and here we have in bracket 2 multiplied by VGS minus VT, and here we have VDS. Okay, now what is the value of VGS here? We know that VGS is equal to VG minus VS. Here gate voltage is 5 and VS is 0, because as you can see here source terminal is grounded. It means the value of VGS is 5 volts. Now what about the value of drain to source voltage? We know that drain to source voltage is equal to drain voltage minus source voltage. Here drain voltage is 0.1 volts and source voltage is 0. It means here drain to source voltage is 0.1 volt. Okay, so this is the value of drain to source voltage. Now we put all the values in this equation A. We have ID is equal to K is 0.5 milliamperes per volt square, and here we have 2 5 minus 1, and here we have 0.1. Okay, so after solving this you will get 0.4 milliamperes. So this is your drain current here. Now we will find the value of drain resistor RD. For this we will use this equation. ID is equal to VDD minus VD divided by RD. Now if we rearrange this equation we get RD is equal to VDD minus VD divided by drain current. Here we know that the value of VDD is 5 volts and drain voltage is 0.1 volts and drain current is 0.4 milliamperes. After solving this you will get 12.25 kilo ohms. Okay, so this is your answer here. Now look at this example. Consider a MOSFET for which minimum channel length L is 0.18 micrometer and channel width is 0.72 micrometer, and here thickness of silicon dioxide is 4 nanometer. Now if you want to find capacitance of oxide layer and total capacitance, so how you are going to find these unknown terms here? First we will find capacitance of oxide layer. We know that the formula of capacitance of oxide layer is permittivity of the silicon dioxide divided by thickness of silicon dioxide. Here we don't know the value of permittivity of silicon dioxide, but it is equal to 3.9 multiplied by permittivity of free space. We know that this permittivity of free space is constant and it has a value of 8.854 into 10 raised to the power minus 12. Okay, so after solving this you will get permittivity of the silicon dioxide, which is equal to 3.45 into 10 raised to the power minus 11 farad per meter. Okay, now we put the value of this permittivity of silicon dioxide in the formula of capacitance of oxide layer. We get this equation. and here we have thickness which is 4 nanometer. Okay, now after solving this you will get 8.6 into 10 raised to the power minus 3 farad per meter square. So this is the value of capacitance of oxide layer. Now what about the total capacitance between gate and channel? It is given by this formula. Here we know that capacitance of oxide layer is 8.6 into 10 raised to the power minus 3 farad per meter square, and here this width is 0.72 into 10 raised to the power minus 6 meter, and here length is 0.18 into 10 raised to the power minus 6 meter. Okay, now this meter and this meter, they will cancel this meter square, and now we will have 1.1 into 10 raised to the power minus 15 farad, and we can write it like this: 1.1 femtofarad. Okay, here this femto is equal to 10 raised to the power minus 15. Okay, so this is your total capacitance here. Okay, now look at this example. If you have a transistor configuration like this, arrow is here, it means it is n-type MOSFET. Here we have source voltage, and here we have drain voltage, and here we have gate voltage. And for suppose here this gate voltage is 3 volts and threshold voltage is 2 volts. Okay, now if drain voltage is 0.5 volts, then what is the mode of operation of transistor here? We know that in saturation region, gate to drain voltage is less than threshold voltage. It can be written as gate voltage minus drain voltage, and it is less than threshold voltage. This gate voltage is 3 volts and drain voltage here is 0.5 volts, and here we have 2 volts. Okay, it is 2.5 volts less than 2 volts. Okay, this condition of saturation region is not satisfied here, but we know that VGD is greater than threshold voltage in triode region. It means here this transistor is in triode region of operation. Now for the same values of gate voltage and threshold voltage, if VD is 1 volt, then what is the mode of operation of transistor here? Again, we know that in saturation region, gate to drain voltage is less than threshold voltage, and it is equal to gate voltage minus drain voltage, and it is less than threshold voltage. Here gate voltage is 3 volts, and here this drain voltage is 1 volt, and this threshold voltage is 2 volts. It means here we have equal potential. It means we can say here transistor is at pinch off point, because here this gate to drain voltage is equal to threshold voltage. Okay, now what is the mode of operation of transistor when drain voltage is 5 volts, and here again gate voltage is 3 volts and threshold voltage is 2 volts. Okay, now we know that in saturation region gate to drain voltage is less than threshold voltage, and here it is written as gate voltage minus drain voltage, and it is less than threshold voltage. This gate voltage is 3 volts here and drain voltage is 5 volts, and here we have 2 volts. It means here we have minus 2 volts, which is less than 2 volts. As you can see here, this condition of saturation region is satisfied. It means here transistor is in saturation mode of operation. Okay, so this is your answer. Now look at this example. If you have a transistor configuration like this, arrow is here, it means this terminal is source. Here we have source resistor Rs, and this is the direction of source current. Here we have source voltage, and here we have drain resistor RD. Here we have drain voltage VD. Here we have VDD, and here we have gate voltage, and this is RG1, and this is gate resistor 2. Okay, and this is again VDD. It means it is a voltage divider by configuration of N-type MOSFET. Okay, now for suppose this RD is 4 kilo ohms. This is the direction of ID. This RS is 6 kilo ohms. This RG1 is 10 mega ohms, and this RG2 is also 10 mega ohms, and here VDD is 10 volts. Okay, so how you are going to start your analysis when K is 0.5 milliamperes per volt square and threshold voltage is 1 volt. Okay, now here first we will find gate voltage VG. Here this gate voltage is equal to this equivalent voltage, and for finding this we will apply voltage divider rule here. Okay, and the formula is Rg2 divided by Rg1 plus Rg2, and it is multiplied by VDD. Here we know that this Rg2 is 10 mega ohms and it is closer to ground, so that's why we are taking the value of Rg2, and here we have 10 mega ohms plus 10 mega ohms, and here this VDD is 10 volts. Okay, so after solving this you will get 5 volts. So this is the value of gate voltage here. Now here we assume that this transistor is in saturation mode. We know that the equation of drain current for saturation mode is ID is equal to K. Here we have gate to source voltage minus threshold voltage whole square. We know that this gate to source voltage is equal to gate voltage minus source voltage, and here we have minus threshold voltage whole square. Here the values of K and gate voltage, they are known, but we don't know the value of source voltage here. This value is also known. Okay, now we call this equation equation A. Now from Ohm's law we know that source voltage is equal to source current multiplied by source resistor, and in field effect transistors we know that gate current is 0 and drain current is equal to source current. It means this equation B can be written as source voltage is equal to drain current multiplied by source resistor. Here we know that the value of source resistor is 6 kilo ohms. It means here this source voltage is equal to drain current multiplied by 6 kilo ohms. This is equation C. Now we will put all the given values in equation A. So it becomes ID is equal to 0.5. Here we have 5 minus ID6 minus 1 whole square. We know that this is Vg and this is Vs and this is threshold voltage and this is the value of K. Okay. Now if we simplify this equation, we get 4 minus ID6 whole square. This is ID. Here as you can see, this term is equivalent to A minus B whole square, and we know that it is equal to A square minus 2AB plus B square. It means this equation now becomes 0.5, and here we have 16 minus 48 ID plus 36 ID square. Okay, and now if we open this bracket, we have 8 minus 24 ID plus 18 ID square. Now we can rearrange this equation like this: 18 ID square minus 24 ID plus 8 minus ID is equal to 0. It means now we have 18 ID square minus 25 ID plus 8 is equal to 0. Now as you can see, this is a quadratic equation here. In our previous slide, we obtained this quadratic equation: 18 ID square minus 25 ID plus 8 is equal to 0. And in order to solve this equation, we will apply this quadratic formula here: b square minus 4ac divided by 2a, and here the value of a is 18, b is minus 25, and c is 8. Now we put all these values in this formula. We get minus 25 plus minus under root minus 25 whole square minus 4, 18, 8 divided by 2 multiplied by 18. Now after solving this, we get 25 plus minus 7 divided by 36. It means here we have two values of drain current. ID1 is 0.889 milliamperes and the value of ID2 will be 0.5 milliamperes. Okay. For first value of drain current, the value of source voltage will be 0.889 milliamperes multiplied by 6 kilo ohms, and it will give us 5.33 volts. And for second value of drain current, the value of source voltage will be 0.5 milliamperes multiplied by 6 kilo ohms, and it will give us 3 volts. Okay. Now we know that n-type MOSFET conducts when gate to source voltage is positive. We know that gate to source voltage is equal to gate voltage minus source voltage. Here we know that gate voltage is 5 volts. Now if the source voltage is 5.33 volts, then the answer will be minus 0.33 volts, and when this source voltage is 3 volts, then gate to source voltage will be 2 volts. It means the value of 3 volts is giving us positive gate to source voltage. It means here the value of source voltage will be 3 volts and the value of drain current will be 0.5 milliamperes. Okay. Now we will find the value of drain voltage VD. For this we will use this equation. ID is equal to VDD minus VD divided by RD. If we rearrange this equation, we get VD is equal to VDD minus ID RD. Here VDD is 10 volts, ID is 0.5 milliamperes and RD is 4 kilo ohms. After solving this, you will get 8 volts. Okay. Now, as we have assumed that here this transistor is in saturation region, and we know that in saturation region gate to drain voltage is less than threshold voltage, and here it can be written as gate voltage minus drain voltage, and it is less than threshold voltage. Here this gate voltage is 5 volts, drain voltage is 8 volts, and threshold voltage is 1 volt, and here we have minus 3 volts which is less than 1 volt. As you can see here, this condition of saturation region is satisfied. It means here our assumption is correct. It means here this transistor is in saturation mode of operation. So this is your answer. Now we will understand transconductance parameters. In our previous lecture, we studied that transconductance parameter K is given by this equation. Okay, now this is MOSFET transconductance parameter. Okay, where this is width of channel, this is length of channel, this is mobility of electrons, and this is capacitance of oxide layer. Now what is process transconductance parameter? It is denoted by this K dash, and this term is process transconductance parameter. It means process transconductance parameter is equal to mobility of electrons multiplied by capacitance of oxide layer. Okay, so this is the difference between MOSFET transconductance parameter and process transconductance parameter. It means MOSFET transconductance parameter can be written as K is equal to half K dash W upon L. Okay, so this is the simplified form of MOSFET transconductance parameter. Okay. Now look at this example. If length of channel is 0.18 micrometer, thickness of oxide layer is 4 nanometer. Threshold voltage is 0.5 volts. Mobility of free electrons is 450 centimeters square per voltage second, and you have to find process transconductance parameter here. Then how you will start your analysis? We know that this process transconductance parameter is equal to mobility of electrons multiplied by capacitance of oxide layer, and here we call this equation A. Now first we will find the capacitance of oxide layer. We know that it is equal to permittivity of silicon dioxide divided by thickness of oxide layer, and here this permittivity of silicon dioxide is equal to 3.9 multiplied by permittivity of free space, which is equal to 8.854 into 10 raised to the power minus 12, and here this thickness is 4 nanometer. After solving this, you will get capacitance of oxide layer, which is 8.6 into 10 raised to the power minus 3 farad per meter square. Okay. Now here mobility of free electrons is 450 centimeters square per volt second. As you can see here, this term is in centimeter. Now we want to convert it into meter. So we get 0.045 meter square per volt second. Okay. Now we have the values of mobility of electrons as well as capacitance of oxide layer. It means now equation A becomes 0.045 meter square per volt second multiplied by 8.6 into 10 raised to the power minus 3 farad per meter square. Okay. After solving this, you will get the value of process transconductance parameter, which is 388 microampere per volt square. Okay, so this is your answer. Now here is your class task. Consider a process technology for which minimum length is 0.4 micrometer, thickness of oxide layer is 8 nanometer, mobility of electrons is 450 centimeter square per volt second, and here threshold voltage is 0.7 volts. Okay, now you have to find capacitance of oxide layer and process transconductance parameter here, and for a MOSFET with aspect ratio 8 micrometer divided by 0.8 micrometer, calculate the values of effective voltage and gate to source voltage that are needed to operate the transistor in the saturation region with a DC drain current ID, which is equal to 100 microamperes. Okay, so this is your class task. That's all for today. Now, what are the key takeaways of this lecture? In this lecture, you solved some examples related to MOSFETs, and you also understood the difference between two transconductance parameters. First is process transconductance parameter, and second is MOSFET transconductance parameter.
Thank you for watching this video. If you have any questions, then write your questions in comment section of this video. Don't forget to subscribe our channel and share it with your friends and family. Thank you.